Hello everyone. Today let us discuss about the combination of resistors, that is series and parallel combinations. Without wasting much time, let's start our discussion. So here I have taken the first case, what that is a series combination of resistors. First thing, let us discuss combination of resistors. When we call them as series, when one end of the resistor is connected to the other end of the resistor, like this, we call it as a series combination. Why we have to connect them in series? Because when we are going to increase the value of the resistance of the circuit, so whenever we get a suitable resistances for the desired value, we can add them all in series so that the circuit will get the appropriate resistance for that with this combination. So because of that, we can connect them in series. So here I have taken two resistors in series. This is R1 and this is R2. Whenever we connect them in series, the first point we have to see is same current flows through them. I value, that is current value, is same in both the resistors. Whenever we connect two resistors in series, current value is always same through both of them. Now potential V is applied to this combination. We have applied a potential V to this combination. Therefore, first and second resistors will not have the same potential. First resistor will have a potential of V1, second one will have a potential of V2. So once again I repeat, whenever we connect two resistors in series, current is same for both of them, but potential is not same. Potential across the first one is V1 and potential across the second one is V2. So let's proceed further. By Ohm's law, we all know the potential across the first one is V1 into IR1 and the potential across the second one is potential across the first one is V1 is equal to IR1, that is equation number 1, and the potential difference across R2, that is equal to V2 is equal to IR2, equation number 2. So potential across the first resistor is V1, which is equal to IR1. Potential difference across the second resistor V2 is equal to IR2, that is equation number 2. Therefore, let us come the total potential V applied across the combination, that is equal to V1 plus V2, but V is equal to I into R, where R is the equivalent resistance, or we can write R equivalent. We can write it as IR equivalent is equal to V1 means IR1 and V2 means IR2, and take I as common in the right side, then R1 plus R2, then both the sides I and I cancel, and finally we get R equivalent is equal to R1 plus R2. This is the derivation for the series combination. This can be extended to any number of resistors as R equivalent is equal to R1 plus R2 plus R3 plus R3 plus etc. Rn. So we can extend to any number of resistors. So this is about the series combination of resistors. So one important point which you have to keep in mind is, first thing is same current flows through each one of them when they are in series, but potential is not same across them. So this is the derivation for series combination. R equivalent is equal to R1 plus R2 plus R3 plus etc. Rn. Now let's go for the next derivation, that is parallel combination of resistors. When we say the parallel combination, parallel combination of resistors. Under that discussion, when do we say that they are in parallel? When both ends of them are added at both the sides, means R1 is there, R2 is there, left end of R1 and left end of R2, they are connected together. Similarly, right end of R1 and right end of R2 are connected together. This combination we call as parallel combination. Once again, the important point to be noted here, whenever they are connected in parallel, potential across them is same now. V is same now. First point to be noted. But current I is not same. Current I is not same. This point we have to remember. So how, like current is just like a water flow, like a river. So I current is coming there and it is divided into two parts. Just like when you can see a stream of water, a river of water is coming and it is divided into two parts, then this incoming water is equal to outgoing water. Sum of the two streams. Incoming stream is equal to sum of the two outgoing streams. In the same way here, we have I is the current which is coming inside. I is the current which is coming inside. After coming to the point A, it is divided into two parts. First part is I1 which is passing through R1 and the second part is I2 which is passing through R2. And again it will join back at the point B. Both of them will join back at the point B and flows out again as I only. So here the point to be noted, once again I repeat, potential is same for parallel combination, whereas currents are not the same for parallel combination of resistors. So this is our point to be noted here. So the charge that flows at A from the left end flows out partly through R1 and partly through R2. So the charge, that means flow of charges, which is called as current, that comes at A, it is divided into two parts. One part flows through R1 and another part flows through R2. The currents I1, I2 are as shown in the figure. So this is I, this is I1, this is I2. So I1, I2 are as shown in the figure. So finally, as I told you, incoming stream is equal to two outgoing streams of water. In the same way, we can say that incoming current I is equal to I1 plus I2. Incoming current I, it comes here and divided into two parts. Therefore, I is equal to I1 plus I2. That is equation number 1 we have written here. Equation number 1. Now, let's continue. Therefore, according to Ohm's law, we all know, according to Ohm's law, we know V is equal to IR. Therefore, potential is same across each one of them. V across the first resistor R1, that is I1 R1, and potential across the second one, that is second resistor, V is equal to I2 R2. V is equal to I2 R2. Therefore, I1 from this equation, I1 is equal to V by R1. Similarly, I2 is equal to V by R2. That we have taken as this equation 2 and equation 3. So substituting them in equation 1 means I is equal to I1 plus I2. Substituting in that, we get I1 means V by R1, I2 means V by R2, and take out V common, we get 1 by R1 plus 1 by R2, that is I. So take V to the left side, we get I divided by V is equal to 1 by R1 plus 1 by R2. but I divided by V, which I am circling with the pink color, that is equal to 1 by R, because R is equal to V by I. Therefore, I by V is equal to 1 by R. So this is equal to 1 by R. This is the derivation for the parallel combination. This is the derivation for the parallel combination. Even though we have derived it for two resistors in parallel, we have derived it for two resistors in parallel, we can extend it to any number of resistors. Suppose if there are n resistors, in parallel, the resultant resistance, that is 1 by R equivalent, resultant resistance of n resistors in parallel combination, 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus etc. 1 by Rn. So this is the derivation for the n resistors in parallel. This is the derivation for the, which I have kept in red color box. This is the derivation for the n resistors in parallel. So finally, I just to give you one tip for entrance exams. Whenever two resistors are in parallel, instead of going for such long formulas, you can make a shortcut formula. R equivalent is equal to R1 R2 by R1 plus R2. Remember, this works for only two resistors, because in examination, whenever you are doing the numerical problems, that is whenever you are attempting JEE mains and then any NEET exam or any other competitive exam, then you can use this formula because it saves your time. How we got it is 1 by R is equal to 1 by R1 plus 1 by R2, 1 by R2, 1 by R2, 1 by R equivalent. Taking LCM R1, R2, here you get R1 plus R1 in the numerator. So reciprocal, or once we take R equivalent is equal to R1 R2 by R1 plus R2. Directly we can use this formula for a combination of two resistors. Why? It will save our time in solving the numericals, especially when the time is running out in the examination hall. That is for competitive exams, you need not show the steps and all. So that time you can use this shortcut formula. So this is all about the series combination and parallel combination. Whenever two resistors are in series, the resultant resistance R is equal to R1 plus R2 plus R3 plus R4 etc. Rn. Whenever resistors are in parallel combination, the resultant resistance is equal to 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 etc. plus 1 by Rn. So these are the derivations for series and parallel combination of resistances. Thank you for watching this video. We will meet in the next video with some other topics, and also we will solve some numericals related to these topics. Until we meet in the next video. Bye. God bless you all.